This is Lab 3 Black Hole. So the purpose of this lab was first to estimate the mass of a black hole using a model with a star in the black hole. The second was to determine the initial velocity of the spaceship required to get close to the black hole and then leave the system using a model with a black hole, planet, and spaceship. And a preview of the main results of the lab with the mass of the black hole and the initial velocity of the spaceship are shown here. So for the main physics concepts, first is Newton's second law, that force equals change in momentum over change in time. And in this lab, it allowed us to set net force equal to the observed change in momentum that we calculated. Uh, Also important are the velocity update and position update formulas, which were used to iteratively model the object's motion in the lab. And the main force in this lab was gravity. The equation is shown right here, and we use this equation to actually solve for the mass of the black hole, and as well as to calculate the forces of all the objects that were interacting with each other. Another important concept is the components of net force. There's the net force in the parallel direction, p hat, which is equal to the change in the magnitude of the momentum over the change in time, and that changes the magnitude of the momentum. And the other component is the perpendicular component in the n hat direction, which points to the center of the turning circle, and that changes the direction of the momentum. So for part one, systems and conditions, the system's a star, surroundings is the black hole, and the initial conditions are shown right here with the mass of the star being 2 times 10 to the 30, the time step being 1 day. So now we're here looking at the code for part one of the lab. Based on the initial and final velocity, we're able to calculate the momentum and then the change in momentum over change in time for this time step, and we're able to set that equal to net force because they are equal to the because of Newton's second law. And after that, breaking it down into components, parallel and perpendicular, we're able to solve for the parallel component using the change in the magnitude of the momentum over change in time. And since the parallel component for the net force is equal to the parallel component of change in momentum over change in time, we're actually able to solve for the perpendicular component just by subtracting the parallel component from the total net force. And after that, we're able to solve for the mass of the black hole, which is just rearranging the gravity formula to solve for the mass of the black hole. And running the program, we can see the arrows that represent the parallel and perpendicular components, as well as the actual net force, the orange one. And you can see that those get a lot bigger as you get closer to the black hole because the magnitude of the force gets a lot bigger. And here we can see the calculated mass of the black hole. It's around 1.4 times 10 to the power of 34 for each time step. And you can also see the results for the net force as well as the parallel and perpendicular components. So for part two, the system was a spaceship. The surroundings were the planet and the black hole, and all the initial conditions can be seen right here with the masses, the initial positions, as well as the initial speeds of the objects. So now looking at the code for part two, right here what we're doing is just calculating the net force on the planet by adding the force from the black hole as well as the force from the ship. And then right here we're calculating the force on the ship by adding the force from the black hole as well as the force from the planets. And then using the velocity and position update equations, we're able to update the position velocity of the planet and the ship. And running this program, we can see that this is what it looks like for the spaceship to get close to the black hole then leave the system. And that would be using a initial velocity I found using trial and error, -5 times 10 to the power of 7 meters per second in the x direction and 2.5 times 10 to the power of 6 meters per second in the y direction. So for sources of error, the mass of a black hole is not exact because we average it, and then there could also be rounding errors. The g constant that we used was also not exact, and these things could affect the calculations. So for what does it mean? The difference between the parallel and perpendicular components for the net force and the change in momentum are that the rate of change in momentum in this lab is the thing that's actually being observed and measured. And after that, we just set the net force components equal to those, because the net force cannot be directly measured without knowing the mass of the black hole first, which is what we're actually trying to solve for. So for what initial velocity would take to enter into orbit, the x and y components of velocity are shown right here, 1.5 times 10 to the 6 and around 1 times 10 to the power of 7. And you can see here that this magenta line here is the spaceship going into orbit with this speed, which is found using trial and error. So yeah, thank you for listening.